Hey everyone, so my name's Mark. I'm product manager at Datadog. I've been at Datadog for over 3 years now, and I've gotten the chance to work on a variety of different tools related to improving developer experience. So the first thing that I worked on was our service level objectives tool, or SLOs, which you use to set and track reliability goals for your applications. That essentially helps an engineering team manage their development priorities as well as their feature development velocity based off how consistent their availability is. Then after that, I worked on an incident management tool that helps coordinate incident responders during an incident response scenario to help resolve a major outage more quickly. And then most recently this year, I started working on static analysis, which is what I'm going to be talking to you about today. So in this talk, we are going to be covering what static analysis is conceptually, why it might be a valuable addition to put a static analysis tool in your workflows, and then we'll even go over at a high level how Datadog went about building its own static analysis tool. Now, for those of you that are familiar with Datadog, you might be kind of confused and asking yourself, like, isn't Datadog an observability company? And it is true. We did get our start in the observability space. But as the company's grown, we have really grown our engineering org, have hundreds of developers now, and you start to run into interesting challenges at that scale. All of that is to say is that we are really passionate about solving developer problems, not because it just helps our customers, but it also helps our own engineers in their own daily lives as well, which is why we set out to build a static analysis tool to complement the observability tools that we already built. So what does this mean practically speaking? So many of you are likely familiar with the DevOps lifecycle diagram shown here. Observability and security tools are typically thought of as being on the right side of this loop. And then tools that are meant more for developers are typically thought of as being on the left side of the loop. And that's where static analysis and the related concept of quality gates that we're going to be talking about today will fall, is on the left side of the loop. And this left side of the loop is where the phrase shifting left or shift left tools comes from. But what's the point? Why is shift left important? Why should you care, basically? And it's really simple. It's much better for organizations to try and catch issues in their code early in the development lifecycle so that they don't have to deal with those headaches in their code later on in runtime when it's in customers' hands. So these issues can range from all kinds of problems in code, like simple code styling issues that make it harder to read code and make it maintainable. There's bugs that cause applications to behave incorrectly. And then worst of all, there are security vulnerabilities that will potentially expose an organization's applications to data breaches. So focusing in on that worst case scenario of a data breach. Security research firm Flashpoint Intelligence in 2022 estimated that there were over 4,000 global data breaches that occurred in that year. And then in 2023, IBM stated that their estimated average cost of a data breach is $4.45 million US, and that figure represents a 15% increase from the same figure from just 3 years ago. So what this tells us is that, one, many organizations will be victims of data breaches every year, and two, that when it does happen, they will pay dearly for it. And keep in mind that with these stats, this isn't really factoring in anything about costs related to bugs or performance issues that cause you to lose customer trust or lost revenue. And this doesn't factor in costs due to maintainability issues that impact dev efficiency, which ultimately impacts an organization's ability to reach its business goals. So that's where static analysis and quality gates kind of come into things. Now, fixing issues early in the development stage is the best place to do it because this is where things are still the most fluid and flexible. The code is still being written, it's still being established, right? So this is the most opportune time to fix a major issue. That being said, if you don't happen to catch all your code issues while you're writing the code, there are many tools out there that will write checks for you and give you insight into issues during your CI pipelines. And it's really not that much more expensive to catch issues here. Now, once you move to a staging environment, things do start to get a little bit more expensive. And in this case, it's still possible to go back and make major changes and go back to the drawing board if absolutely necessary. And then once you reach production, that's when things get really expensive and a big spike happens. And the main reason is because at this point the code is live and in customers' hands. So there's not just costs related to development effort anymore, there's costs related to lawsuits, legal fees, loss of revenue, things like that. So that's why shifting left is imperative and where static analysis and quality gates come in. So static analysis can basically act as your investigator. It searches your code files without having to run the application, and then basically tells you if it finds any code issues. And then if static analysis ends up being your investigator, quality gates are basically your enforcer. So they prevent bad code, as determined by checks from various tools, including static analysis issues, from being able to be merged into production. So to visualize this further, the kind of automation that we can set up here is that static analysis can be placed in different stages of the software development lifecycle, and then we get warnings in whatever stages we choose to establish it in. Then quality gates basically make sure that we respect those warnings and acts as the last line of defense. And then modern static analysis tools will typically integrate with different dev tools, and that gives us the benefit of being able to speed up the code review process while also maintaining an organization's quality standards or security practices. So in other words, the benefits of having static analysis and quality gates working in tandem look something like this. So hopefully no one's getting mad at me at this point for suggesting that anyone in this room could be writing bad code, but essentially the point here is when you're writing code, the reality is that it's very easy to make a variety of simple blink and you'll miss it mistakes that are really tedious to find and correct that can still cause potentially large consequences within our applications. So I'll use myself as an example. Back when I was first learning programming in school, I learned C++, and I got seg faults and all kinds of issues for what usually ended up being very simple one-line mistakes. And obviously, even though it was a one-line mistake, it would still take quite a lot of time to find the issue, and then it would be really frustrating to figure out what the problem ended up being the entire time. So to kind of establish this further, we've got kind of a demo scenario here where I have a demo repo that's hosted on the Datadog GitHub organization that you can follow along with. And we have our JetBrains integration, which is completely free to use. You don't have to be a Datadog customer or anything like that. It's something that we want to provide to the community to run static analysis with. And essentially the way that it works is it runs as a binary that is running locally in your machine. So in the demo repo, there's 3 example files where we're going to go over simple mistakes that a developer could make, that a static analysis tool could check, and that a quality gate rule could be set to block from reaching production if we really wanted it to. So in this first example, the service.py, there's a simple poor practice here. At the end of the file in lines 18 and 19, we could make this for loop less verbose by stating it as for I in products, and then the print statement could replace the current statement with just I.name. This is a really simple best practice that developers should be making to make their code more legible. But it's easy to forget all of these best practices, especially if you're a new programmer or you're coming from a different, older language that didn't have these nice simplified syntaxes. Then the second example is in a file called api.py, where we have a safety issue. And the safety issue is on line 6, where we're missing a timeout parameter in our GET request. Now, by default, the requests module in Python doesn't set timeouts for the requests that we're making. And the consequence of that is if we forget to add a timeout, like we've done here, we will end up potentially dealing with hanging connections. And then too many hanging connections could cause the server to overload or crash just because of this one line of code. And then finally, the third example is in a file called database.py, where we have a security vulnerability. And that's on line 20, where we're using an unsanitized string to make an SQL query, which could expose this application to potential SQL injections. So again, really simple mistake on a single line of code that any developer could make, especially an inexperienced developer. So we've established what static analysis is and why it might be helpful in your workflows. Let's see these examples using real tools in real life. So obviously today, I'll be going over Datadog static analysis and what we built internally. But these concepts are really applicable to any static analysis tool that you might be seeing out there. And the first step that I need to do is I need to configure my repo. So essentially what I need to do here is I need to pick my language that I'm going to be scanning. So in this case, it's going to be Python. And then I need to specify what it is that I actually want to check my code against. So I'll start off with just basic code quality and security rules, but there are some rule sets here related to specific Python frameworks as well, but we'll just keep it to the default. And basically, this just suggests a YAML file. I'd copy this YAML file, put it in the root directory of my repo, and this basically just tells the static analyzer what kinds of checks I want to be scanning my code against. Now, if we want this to be available and consistently applicable to all the engineers working on a particular repo, we can put static analysis checks in our CI provider. So in the example today, I'm using GitHub Actions, but most static analysis tools will typically offer a generic CLI tool that will allow you to just add these checks to any CI provider that you might be using. So I won't bore you with the setup process much longer at this point, and I'll instead switch over to the earliest stage of the development lifecycle, which is in my IDE, which in this case is IntelliJ. So again, the IDE integration that we have here is free. You don't have to have a Datadog account to use it. And basically, the way that it works is I have my static analysis YAML file set in the root directory of this repo. So it tells the analyzer what it is that we want to check our code against. And then the analyzer itself, like I mentioned earlier, is running as a binary locally on our machine. So I'll start off with my first file, where I have that verbose for loop. So this highlights the issue as I'm editing this file as a problem in IntelliJ, which gives me the red squiggly that calls my attention to it so that I notice to fix it. Then a lot of static analysis tools will also provide suggested fixes for these issues. So I can just hit this button or use the keyboard shortcut in the IDE, and then it will just replace the lines of code and fix them for me so that I can save the extra seconds or minutes from having to type that out myself. Then when I switch over to the API.py file, I have that request missing timeout parameter again. And like before, I can just add a suggested fix here, and then that will add a timeout of 5 seconds if I need it. So I'm actually going to undo this change because I kind of want to show what happens if I wasn't paying attention to these squigglies or I forgot to fix this issue, what's going to happen later down the line in the software development lifecycle. Then when I switched to our last file, database.py, got that SQL injection issue there as well. Now for this one, it's not as easy for us to templatize a default suggested fix beforehand because the solution to this problem really depends on the structure of the query that we're trying to make, as well as the framework that we're using to make the query. So the benefit here still is that we at least get the squiggly to call our attention to it so that we can fix this issue manually if need be. So then from there, I've purposely left 2 of these issues in place without fixing it, just fix the for loop problem, and I can just stage these changes and then add them to commit if I want to. So one thing to note is there is the option of being able to set Git hooks for pre-commit or pre-push that would prevent issues like this from being able to be pushed to origin or be added to our commits. I'm not going to show how we set that up here, but it is an important tool to remember that is in our toolkit if we want to. And again, that's something that any user can set up by themselves. So there is a SaaS portion to this that I'll cover that adds a little bit more visual element to it outside of the IDE. So if I switch over to this pull request that I have, it's got the same changes that I had before in my development branch in the IDE, and it's showing it in my GitHub PR here. So basically what happens is I've got, let me zoom in a little bit here. So I've got 2 failed checks here for my quality gate. So if I switch over to the details of that quality gate, I see that, as expected, these are the 2 issues that I forgot to fix earlier on, and that I can also see the matching events in Datadog as well, where it gets filtered to the commit that's relevant to this particular PR. And again, seeing the same 2 issues that I would be expecting to see here. Now, in the case of the SQL injection, I'd be remiss to not mention GenAI at some point in this presentation. So essentially, when we don't have a templatized fix beforehand, we can use OpenAI GPT-4 to basically take the context of the query that we're making so that it provides us with a suggested fix directly here that we could then copy, paste, commit to resolve this issue. And then similarly, for the timeout error, that default fix is also there as well to add the timeout parameter, the same one that we saw in the IDE earlier. Now, for the gating solution that failed the check in the PR in the first place, you could really do this with a simple script that you add to your CI pipelines. And in this case, really the chief difference with using quality gates in Datadog, for example, would be you just get a UI to configure the rules instead of having to code it up yourself. So I'll zoom in again here. And in this case, the rule that failed is just checking for the highest level of highest severity level of static analysis violations, checking if there's at least one of them, and then if it belongs to the security category. And if these conditions are met, then it will block our gating behavior, fail the check so that we can't merge that code into production. So again, these concepts are pretty similar, like across various different static analysis tools out there. Now, I did say earlier on that I would cover, at a high level, how we built this, right? So I know we're at a Python conference. Unfortunately, I do have to admit that we didn't end up building the static analyzer in Python. Python's obviously a great language. It's very versatile, but it just wasn't the right tool for the job in this particular instance. And really, the requirements that we set out for with the static analyzer is that it needs to be fast and portable. Fast because we obviously want these checks to complete quickly so that no engineer is sitting around waiting for the checks to complete so that they can move forward and get feedback on their code right away. And it needs to be portable because, again, we want this to be able to run locally on user machines as part of the IDE integration. And that entails having to export the analyzer to various CPU architectures, which is a big deal nowadays, especially because ARM is really making a comeback in personal computers, especially with the Apple Silicon and in newer MacBooks and other Mac devices. And then the second thing was broad language support. We want to be able to parse many different languages and technologies where we want to write rules for best practices and security without having to put in a lot of effort to build our own parsers for every single technology. And then finally, we wanted to make it easy to write as many rules as we can that are high quality, have low false positive rate, so that we can check for a variety of different issues that would exist in various tech stacks. So the static analyzer architecture basically looks a little bit like this. So the green nodes here represent actions, and then the orange nodes represent artifacts that are either inputs or outputs of the system. So the green, so in this case, before we can actually analyze any code, what we need to do is we need to get the abstract syntax tree of the code and then search for the nodes that we're interested in checking for best practices or security vulnerabilities with the rules. So we get that query, which outputs AST nodes, and then combined with whatever rules we write, that's what allows us to analyze the code to see if there's any violations or not. And if there are violations, that is the output of the system that ends up getting displayed to the end user. So the solution that we ultimately went with was to write the static analyzer in Rust, because Rust is very fast, and it also made it easy to export the analyzer to binaries for different CPU architectures. And for our AST parser, we chose this really cool open source library called TreeSitter, which has support out of the box for like hundreds of different programming languages and technologies. And the real benefit of that is that meant we didn't have to write individual parsers from scratch one by one for every language that we want to write rules for. And then to make writing the rules themselves easier, we built our own custom rule editor that our engineering team uses to write the rules themselves for the different languages. And that rule editor looks like this. So what I'm showing here is the same missing timeout request in the Python request module example that we were covering earlier. And the rule editor is basically split up into 4 sections. The first section is the TreeSitter query, which is written as an S expression. And in this case, what it's looking for is it's checking first that the request module itself is even being imported in the code snippet that we're scanning. And if it is, it's going to look for AST nodes related to function calls, to .get, put, things like that. And then it takes those nodes that it returns and passes it to the business logic of the rule, which is written in JavaScript, and it's found in the green right below the TreeSitter query. This rule code basically will take the AST nodes that we get, and then it will essentially apply the business logic to determine if there's violations in those nodes or not. Then, in the blue on the top right, we have any number of test cases that we want to use to test edge cases of what this rule should be finding. So if we purposely have a file that doesn't have violations, we would expect the analyzer to report no violations. And if we have one or more violations, we would expect it to return the correct number of violations that we purposely wrote into the code snippets. And then finally, in the black underneath the test cases is the output that TreeSitter produces. And this is basically our AST format that TreeSitter produces. And the benefit of this is it allows us to fine-tune our TreeSitter query to make sure that we're actually getting the right nodes from the test case example that's shown above. So this AST is specifically for whatever test case is in focus above in the blue. So the benefit of all of this is that we can write the logic and query for the rule, and then test and iterate on it all in one page, which allows us to minimize false positives, and then also add new test cases if we ever find a new false positive later, and really makes writing rules that much simpler because we get everything in that single view like this. So it's been an exciting thing to work on, and ultimately, what we're looking forward to is continuing to figure out how to harmonize static analysis with our runtime monitoring tools to help not only our customers, but our own engineering teams in shipping performant and secure applications. So yeah, I'd like to thank you all for listening. And if you're interested in learning more about our static analyzer, it's also open source, the Rust analyzer that I was talking about before. So you can go to our GitHub, check it out, see how we built it for yourselves. And then I'm bringing up the same QR codes for the demo repo and the JetBrains integration as well for anyone who maybe didn't get the chance to scan it earlier on in the presentation. So yep, thanks again, and have a good rest of your day.
Thank you, Mark. We have up to 10 minutes for questions.
Hi. So you showed language models suggesting fixes to problems brought up by the analyzer. Because you can't get 100% coverage of every mistake a developer is going to make, do you think there will be a point where language models will be used to actually spot these issues in the near future or far future?
Potentially. We haven't really done like a lot of testing on the accuracy of that, so it's not really something we've experimented at this time. But obviously, we see that like the different like OpenAI, all the other companies are continuing to improve the models. So maybe in the future it will become, accurate enough to do that. But it's not something that like we've really looked into today for now.
Hi, small question. When you put the static analyzer into the CI system, and there were some of the suggestions were if you choose not to use the suggestion, is like for example the SQL injection, right? So it's like you could choose not to. So it's not evident that you. So how can we get along like not to allow committing to the repo? Like how can we add an exception and move ahead kind of thing?
Oh, yeah, so in general, when it comes to, like, I think you're referring to the quality gates piece, right? Yeah, okay. So quality gates really can be something as simple as you write your own script that you put in your CI provider. Really, the only difference with what I was showing here is just there's a UI around it, basically. So instead of coding up the script yourself, it basically, you just pick the conditions that you want for the violations to match against, and then it's just we have a CLI tool that you basically just put into your CI that when the condition matches, that'll be what fails the check. But again, you could write scripts yourself for these checks if you really wanted to as well. Yeah.
Cool. Thank you. Any other questions?
Hi, thanks for the presentation, really great. I wanted to ask you, do you have experience with introducing such practices in a team where there's, let's say, a huge monorepo with a lot of legacy code that hasn't gone through static analysis or a lot of code reviews in the past? And how did you fight the feedback?
Yeah, I mean, I think the hardest challenge with it is just like propagating the knowledge the tools in place, because if you're at a large organization with a large monorepo that a ton of people are using, like informing everyone is basically like is kind of the difficult part. When it comes to something like, I think the checks themselves kind of advertise themselves because you see the red X's and stuff like that in GitHub. And the thing that's important to know about these checks is they don't have to be blocking right away. So for example, in the scripts that you write or the example shown here, you can set them to be non-blocking so that you can just get people adjusted to things. And then once you think there's like a decent comfortability, or people are comfortable that know that it's in place, you can then switch it to blocking. So I think that's probably the best piece of advice is probably don't start in a big mono repo like that where it's like tons of people that are working on it. Don't start by actually blocking anyone at first. Let people know that like this is something that you want to roll out. It's a tool that you want to add to your development lifecycle. Make it non-blocking at first. Once people have given you feedback, things are comfortable, then switch it to blocking. How long that process takes, hard to say. It's really just going to depend on the circumstance of how long it takes for people to be onboarded to it, basically. Yeah.
Can I ask a follow-up? Oh, yeah. I have a follow-up, which is the code base that already exists versus new additions. So would you run only on the new additions, so new features or bug fixes, the static analysis, or would you run it on the whole legacy code every single time you introduce it into a repo?
Yeah, that's a good question. So for example, when I was in IntelliJ, it's only scanning for violations in the file that I'm actually editing. So that portion is focused on just like new changes, right? It's not gonna scan the entire repo and then give you like a big list of issues that have nothing to do with the project that you're actually working on. But you can also do like a full repo scan and then see in the list view page or things like that to be able to see all the violations that exist like on the full repository. So both, like depending on what you're looking for.
Okay, cool. Thank you.
Yeah.
Okay. Thank you so much, Mar.